The science of aging has long sought to answer why some people not only live longer but age with remarkable resilience, free from many of the chronic diseases that typically accompany advanced years. While genetics play a role, recent advances in epigenetics, the study of heritable changes in gene expression that don't involve alterations to the underlying DNA sequence, suggests that how we age is far more malleable than once believed. It turns out that our environment, behaviors, diet, stress levels, and even our relationships leave molecular marks on our genome, influencing how our genes are turned on or off throughout life. These epigenetic modifications help explain why identical twins can age at different rates, why some individuals remain cognitively sharp into their hundreds, and why long-lived populations like the centenarians of southern Italy appear to carry distinct molecular signatures that reflect not only their genes, but their lifelong habits. At the heart of this process are chemical modifications like DNA methylation and histone acetylation, which act as switches and dimmers for gene activity. Over time, a person's epigenetic landscape changes. Some genes become silenced, others become overexpressed, and the cumulative effect can either accelerate aging or buffer against it. In unhealthy aging, these changes often reflect chronic inflammation, oxidative stress, poor metabolic regulation, and impaired cellular repair. But in healthy aging, especially as seen in centenarian populations, the epigenome appears more stable, more balanced, and more protective against the typical hallmarks of aging. Centenarians from regions like Salento in southern Italy offer a living example of this principle. Studies conducted in recent years have found that many of these individuals exhibit epigenetic markers associated with youthful gene expression patterns, despite their advanced chronological age. Their epigenetic age, measured by algorithms like the Horvath clock, which estimates biological age based on methylation levels, often lags behind their actual age. In other words, their bodies behave molecularly as if they are years, sometimes decades, younger. Why this happens is a question of great scientific interest, and much of the answer appears to lie in lifestyle. The Salento centenarians follow many of the core tenets found in longevity hotspots worldwide: a minimally processed, plant-rich diet high in extra virgin olive oil and seasonal vegetables, daily physical activity that is functional rather than structured, strong family and community ties that provide emotional support and reduce loneliness, and a relatively low-stress environment. These factors don't just feel good, they have measurable biological impact. For instance, polyphenol from olive oil and herbs common in Mediterranean cooking are known to influence epigenetic mechanisms related to inflammation and cellular repair. They may help maintain telomere length, protect mitochondrial function, and even activate longevity-related genes such as SIRT1, a key player in cellular stress resistance. Regular movement improves metabolic health and triggers the release of signaling molecules like irisin, which has been linked to neuroprotection and reduced DNA methylation drift. Even psychological factors, like having a strong sense of purpose, something common among these centenarians, are associated with favorable gene expression profiles related to immune function and stress resilience. Environmental exposures also play a powerful role. Unlike urban settings with pollution, endocrine disruptors, and constant sensory overload, the air, water, and soil in rural Salento are relatively clean and stable. This minimizes toxic burden and supports a more favorable epigenetic environment over the lifespan. Additionally, growing evidence shows that intergenerational epigenetic inheritance might also contribute. Children of centenarians often show signs of slower biological aging themselves, even when raised in different environments. What's most striking is that these epigenetic advantages are not exclusive to those born in longevity hotspots. Research suggests that epigenetic patterns are highly dynamic and modifiable, even in adulthood. People who adopt healthier lifestyles can reset some aspects of their biological aging. In clinical trials, interventions such as plant-based diets, regular moderate exercise, improved sleep, and stress-reducing practices like meditation have been shown to slow the epigenetic aging process, sometimes within months. One notable study published in Aging demonstrated that participants who followed an 8-week lifestyle program combining nutrition, sleep, and stress management reversed their biological age by over 3 years on average. This malleability of the epigenome is one of the most hopeful frontiers in modern aging science. It reframes aging not as a passive, genetically determined decline, but as a dynamic process that can be shaped by the choices we make every day. It also explains why two people of the same chronological age can look, feel, and function so differently. Not only are their lifestyles different, but their genes are responding differently to the lives they lead. As research continues, epigenetic biomarkers may soon become central tools in preventive medicine, offering personalized insight into one's health trajectory and helping to tailor interventions that optimize not just lifespan, but health span. And while the future may hold pharmaceutical agents that mimic the epigenetic benefits of healthy living, the centenarians of Italy remind us that the blueprint for long life is already available to us, woven into our meals, our movements, our relationships, and our environment. In that way, the science of epigenetics doesn't just illuminate how we age, it offers a roadmap for aging well, built not from futuristic medicine, but from the wisdom of cultures that have always lived in harmony with nature and community.